Welcome to my YouTube channel. Our topic for today is Riemann-Stieltjes integral and its various generalizations. We'll begin with some definitions that will help us through the course of this lecture. We are going to define partitioning of intervals. Let I be a non-empty compact interval. A partition of I is a finite collection of almost disjoint non-empty compact subintervals whose union is the interval. A partition of AB with subintervals ik is determined by the set of endpoints of the intervals. We will denote a partition P either by its intersect P or by the set of endpoints of the interval. We will adopt either notations as convenient. The context should make it clear which one is being used. There is always one more endpoint than intervals. Now let's look at the set of intervals 0 and 1 over 5, 1 over 5 and 1 over 4, 1 over 4, 1 over 3, 1 over 3, 1 over 2, close interval 1 over 2 and 1 is a partition of 0, 1. The corresponding set of endpoints is 0, 1 over 5, 1 over 4, 1 over 3, 1 over 2, and 1. So we have been able to partition the interval 0, 1 into equal subintervals from 0 to 1. We denote the length of an interval I by the absolute value of I, which is b minus a. So in this case, interval 0 to 1, our a will be 0, our b will be 1. Note that the sum of the length ik, absolute value of ik, of the almost disjoint subintervals in a partition of an interval I is equal to length of the whole interval. This is obvious geometrically. Algebraically, it follows from the telescoping series, where the summation of the intervals will now give us the interval itself. And we are going to define the Riemann integral. It is assumed that we are familiar with the Riemann integral, but let's go through it briefly before going to Riemann-Stieltjes because they are similar. We define the upper Riemann sum of f with respect to the partition P by U, F, and P. And we also define the lower Riemann sum with respect to the partition by L, F, and P. Now, suppose that a function is bounded on the interval AB, where AB is in R and A is less than B. Suppose further that we have a partition, then the LFP will become the summation of the partition times the infimum of f of x, and the UFP will now be the summation of the partition times the supremum of the f of x. So this LFP and UFP is what we call the lower Riemann sum and the upper Riemann sum. So if the upper Riemann sum and the lower Riemann sum are equal, then you say that the function is Riemann integrable. Then if they are not equal, then they are not Riemann integrable. Similarly, if you are Riemann-Stieltjes integral, if the lower double sum is equal to the upper double sum, then you say that the function is Riemann-Stieltjes integral. But if the lower double sum is not equal to the upper double sum, then it is not Riemann-Stieltjes. Now, Riemann integral, we have already defined what the Riemann sums are, the upper and the lower Riemann sums. If in addition their limits are the same or exist, then we say that the f of x is Riemann integrable, and we'll write it as f of x in R of AB. Let's take a very simple example. Consider the function f of x equal to x squared in the interval 0, 1. Suppose that n is given and fixed. Let us consider the partition from 0 to 1 of the interval, and that partition is I minus 1 over n, I over n, for every I running from 1 to n. Now, what would the infimum of f of x be? The infimum of f of x would be I minus 1 all squared all over n squared. while the supremum of f of x will be I squared over n squared. Now, the lower sum will now be the summation of the intervals times the infimum of f of x. And when you do that properly, for the example at hand, you're going to have that the lower sum will be 1 over 3. Similarly, the upper sum, when you apply it to and simplify properly, you're also going to get 1 over 3. So note that the lower sum is equal to the upper Riemann sum, and that both terms converge to 1 over 3 as n goes to infinity. Thus, the function f of x equal to s squared is Riemann integrable on 0, 1. And the Riemann integral is 1 over 3. Let's take another example. This time, the same function, but the interval is from 0 to 2. Partition well defined, and we are taking the partition this time to be 2 in bracket I minus 1 over n, comma 2i over n, for every I running from 1 to n. Now, the infimum of f of x is 4i minus 1 squared all over n squared, and the supremum is 4i squared all over n squared. Now, the lower Riemann sum will now be the summation of the interval times the infimum of f of x. And when you take the product and simplify properly, you are going to get 8 over 3. Similarly, the upper Riemann sum, when you multiply the interval, sum of the interval to the supremum, you're also going to get 8 over 3. So note that the lower Riemann sum is equal to the upper Riemann sum, and that both terms converge to 8 over 3 as n goes to infinity. Thus, the function f of x is equal to s squared. Is Riemann integrable on 0 and the interval 0, 2. Riemann-Stieltjes integral. Let g of x be a monotone increasing function on the interval, then let p be a partition on ab, then the difference in gr will be gxr minus gxr minus 1. It's always positive because it's a monotone increasing sequence. Now, let f of x be a bounded function defined on the interval ab, closed interval ab. We'll define u of p of fg as the summation capital MR difference of gr, while the L of pfg is small letter m difference of gr. Now, the upper Riemann-Stieltjes integral of f of x with respect to g of x is defined as this integral from a to b. That b has a bar on top of it. That is a notation for upper Riemann-Stieltjes of f of x d of g of x. Okay, is actually equal to the infimum of u of pfg, and that infimum is what we call the upper double sum, while the lower Riemann-Stieltjes of f of x with respect to g of x is defined as this integral from a to b. You see that the a has an underline, and it is the supremum of the lower Riemann-Stieltjes. So that supremum of the lower Riemann-Stieltjes is what we call the lower double sum. If the upper and lower Riemann-Stieltjes integral are equal, then we say that the function f of x is Riemann-Stieltjes integrable with respect to g of x over the interval ab. Let's take an example. We want to evaluate the integral of 0 to 1 of x with respect to s squared. You are integrating x, but with respect to s squared. That is the difference between Riemann integral and Riemann-Stieltjes integral. Okay, yeah, you're differentiating with respect to a function. You're differentiating a function with respect to a function. So that is the idea. So, and that with respect to a function is the one we now call the g of x. F of x is x, while the g of x is the s squared. So here, f of x is x and g of x is s squared. Clearly, f of x is continuous and g of x is monotonic on 0, 1. Hence, f is Riemann-Stieltjes integrable over G on 0, 1. So let's move on. Let P be any partition on 0, 1. That is, this is how we get the partition B minus A over N. So our A here is 0, our B here is 1. 1 minus 0 is 1 over N. So the partitioning will go in 1 over N. Therefore, P will now be arrow minus 1 over N, comma, arrow over N, for all R equal to 1 to N. Now, the difference in GR for this particular example will give us 2 arrow minus 1 over N squared. While capital M R, which is the supremum of f of x, will give us arrow over N. That is the supremum. While the infimum, the small letter m r, will give us the infimum of f of x, which is arrow minus 1 over N. Remember, in the interval, you have 1 that is arrow minus N, r minus 1 over N. Then you have the supremum of to be arrow over N. In every interval, there is an infimum, there is a supremum. So that is how we arrive at those supremum and the infimums. Therefore, the upper double sum of the integral from 0 to 1, you will see the bar on 1, is take the limit as n goes to infinity of the summation of capital M R of difference of GR. And that limit is what we are seeing now, which is the summation of r over n times 2 r minus 1 over n squared. And when you open it up, you're going to have the limit of 1 over 3 n raised to power 3 summation to r squared minus r. And when you go on to evaluate properly and factor out, you're going to have the upper double sum to be 2 over 3. Similarly, we are going to look at the lower Riemann-Stieltjes, or the lower double sum. Now, when you take the limit of the summation of small m difference GR, you're going to have this limit as n goes to infinity of summation of r minus 1 over n times 2 r minus 1 over n squared. And when you evaluate properly again and factor out, you're going to have 2 over 3. Therefore, this integral from 0 to 1 of x with respect to s squared will give us 2 over 3. So according to the Riemann-Stieltjes integral, the function is Riemann-Stieltjes and the integral is 2 over 3. Now let's look at another example. Evaluate integral 0 to 2 of f of x dgx, where f of x is s squared and g of x is s squared, using Riemann-Stieltjes integral definition. Now, our f of x is s squared, g of x is s squared. So you are integrating from 0 to 1 of s squared with respect to s squared, using Riemann-Stieltjes. Here, f of x is s squared and g of x is s squared. Clearly, f of x is continuous and g of x is monotonic on the interval 0, 1. Hence, f is Riemann-Stieltjes integrable over g on 0, 2. Now, how would the partitioning look like? Let P be any partition on 0, 2. That is, when you subtract, you have 2 over n. You now multiply the 2 over n to r minus 1 and to r. So you're going to have 2 over 2 times r minus 1 over n as the inf and 2r over n as the supremum for all r equal to 1 to n. Now, the difference in GR, when you do it properly, you're going to get 4 times 2r minus 1 all over n squared. And capital MR will be the supremum of f of x, which will give us 4r squared over n squared. Small mr, which is the infimum of f of x, will give us 4r minus 1 squared all over n squared. Therefore, this integral from 0 to 2 of f dg, finding the upper double sum, will give us the limit as n goes to infinity of the summation in bracket for r squared over n squared times 4 times 2r minus 1 over n squared. And you continue simplifying, you're going to have 16 over n raised to the power 4 will factor out, and you have summation of 2r raised to the power 3 minus n squared. And when you continue simplifying, you're going to get 8. You're going to get 8 for the upper Riemann-Stieltjes. Now the lower Riemann-Stieltjes, you're going to have this following the similar full step from the other. At the end, we'll factor out 16 over n raised to the power 4 and take the limit also. We are going to get 8. So thus, this integral from 0 to 2 of f of x dg of x is actually equal to 8, where f of x is x squared and g of x is x squared. Continuing with more examples, if f is bounded on AB and c is constant, then evaluate the integral of f dc over the interval AB. Solution, or in this case you can even say proof, but let's move on. So using the definition of Riemann-Stieltjes, this is what we are going to have. Okay, that summation of f tr times difference of gr, and when you continue the simplification, you're going to have gx minus gx minus 1. Both of them are constants, so that is why you now have c minus c at the end, which will give us 0. Therefore, the integral of a function with respect to a constant using Riemann-Stieltjes is 0. Then properties of Riemann-Stieltjes integral, we are going to look at some few theorems. Let C1, C2 be two constants in R. If Fg is Riemann-Stieltjes in arrow alpha on AB, then C1F plus C2G will still be Riemann-Stieltjes. And the integral from A to B summation will also be, we'll factor the constant out, C1 over the integral plus C2 over the integral. Another property is if F is Riemann-Stieltjes and F is in the summation, then the integral in 2 holds and the one in 3 holds. 1, 2, 3 are actually similar but in different expressions. So all the 3 are the same and they all hold for Riemann-Stieltjes integral. Now, technique of integration under Riemann-Stieltjes, we still have integration by parts, which we are very familiar with. So this is how the theorem on integration by parts is defined. So if f is Riemann-Stieltjes, then alpha is Riemann-Stieltjes, and this integral using integration by parts will now mean f of b times alpha b minus f of a times alpha a minus the integral over ab of alpha x d f of x. Let's take an example. Say given that f of x is equal to x and alpha x is equal to x plus the greatest integer function of x. Consider this partition from 0 to 10. Then find the integral from 0 to 10 of f of x d alpha x. Now using our integration by parts, it's going to look like this. Say integral from 0 to 10 f of x d alpha x is equal to, by the time you do all your substitutions properly as given, you're going to have 105. So this one is shorter is shorter and easy to implement. Another theorem called the change of variable under Riemann-Stieltjes says suppose that f is Riemann-Stieltjes and g is strictly increasing continuous function with a equal to gc, b, gd, let h be f composite g and beta alpha composite g, then h is Riemann-Stieltjes. So we can use change of variable written this way, that the integral of a b of f of x d alpha s is equal to the integral of cd then of f of gt d alpha gt, and it will still be the same thing as integral of cd of ht d beta t. Example, let y equal to square root of x. We have f of x equal to the greatest integer function of square root of x plus x squared and alpha x equal to square root of x. Now applying the change of variable tactics, this is what you're going to have, and when you simplify properly, then you're going to get 37/5. Thank you for listening.